Well, hello, and welcome to another video on where I'd like to demonstrate how to solve a thermodynamics problem using MATLAB. So let's go ahead and get started. This is going to be problem 355 out of the textbook. And this problem is going to require the evaluation of thermodynamic properties where you're going to use your steam tables. And so what I'm going to try to do is illustrate how to leverage some work that I've done for you and myself in MATLAB and saved it to a file. So this is going to be problem 355. So let's quickly review what it takes to solve a thermodynamic problem in the first place, not just jumping right to MATLAB. So remember, you're going to read the problem in the words, then you're going to draw a sketch and study that sketch to plan your work before you put pencil to paper or before you start writing MATLAB code. And then finally, you're going to either solve the problem with pencil and paper, or in this situation, solve the problem by writing MATLAB code. So let's keep that in mind. It's not a matter of just going right to MATLAB and jamming in numbers. So let's look at our problem 355 from the textbook. I'll read it. Hopefully you'll read along. And wow, look at this situation. You've also been provided a sketch. And so that's going to speed our planning, I believe. 1 pound mass of water is contained in a piston and cylinder assembly, and it undergoes a power cycle as shown in the figure. For each of the 4 processes, evaluate the work and the heat transfer, and it's saying evaluate that in the units of BTUs. All right, so let's plan our work. So the first thing is, what are we seeking to find? We're seeking to find the work and the heat transfer for each little process, 1 to 2, 2 to 3, 3 to 4, 4 to 1. Another thing, reading the problem, it says 1 pound mass, piston and cylinder. That I'm going to write down on pencil and paper outside the MATLAB environment. Closed system, M equals 1 pound mass. Okay. We'll observe that we're going to be using English units. So when we access the steam tables, we're going to have to be sure that we're working in English units. Let's see. Probably, I think you've gotten enough experience now to know that when you're asked for work and heat transfer, you're going to work on the work first for a closed system, because you know that for any quasi-equilibrium process for a closed system, the workout is integral PDV, and then recognizing the definition of volume, you can say that's equal to M, the mass of the closed system, integral PD little v. So that tells us we're going to need to draw a PV diagram to visualize the work for each process. We can't visualize the work using a TV diagram because that's not what the integral says. Heat transfer, how are we going to find heat transfer? Based on what we've learned so far in class, you're going to write out the first law. Since you can find the work out, then you can write the first law. It says Qn minus W out equals delta U plus potential and kinetic energy change, which we are not going to consider for this problem. And that's equals M, the mass of the system, times delta little u. Okay, so that's pretty good planning. Now let's plan our work sort of in detail. Well, let us draw our pressure volume diagram with the vapor dome and translate this process, this cycle, over to here. Well, we see we're going to start of 1, saturated liquid. Okay, there's 1. 2, constant temperature, saturated vapor. Okay, so remember, under the dome, the pressure and the temperature are dependent variables. That's how we know. That's also a horizontal line on a PV diagram. 2 to 3, constant volume, given constant volume. So we'll draw constant volume line coming down to a lower pressure. I'll label that 70 psi here on my pressure volume diagram. Constant temperature, i.e. constant pressure, 3 to 4. And again, given constant volume process, 4 to 1. All right, so now we've got a pretty decent PV diagram. Let's quickly study our PV diagram. to look at the work done for each process. Okay, 1 to 2, 1 to 2. That's the area under the curve, integral P dV. Well, that's just a rectangle, and we're integrating left to right. The work out's going to be a positive number. How about 2 to 3? Well, we don't need MATLAB to indicate that the work out from 2 to 3 is 0. In fact, we're going to put that in as a known value in MATLAB. 3 to 4, integral P dV. Well, that's going to be the area under the curve, 3 to 4. It's going to be another little rectangle. Okay, but look, we're integrating right to left, so the work out from 3 to 4 is going to be less than 0. How about the work from 4 to 1? Again, dV is 0, no change in volume. So the work out from 4 to 1 is 0. And now let's look at the net work for the cycle. This is going to prepare you for future analyses in thermodynamics class. The net work is the shaded area bounded within the cycle itself, and we can observe since the direction of the cycle is clockwise, you can show and satisfy yourself that for this clockwise direction of the process cycle, the net work is greater than 0. You're going to get a positive number for the net work. Let's keep planning what we need to do in MATLAB. Okay. State 1 is saturated liquid at 700 psi. If we're going to the back of the book, we'll use the pressure table and look up V sub F and also U sub F for the first law. Okay, state 2, saturated vapor. Again, we're just going to look up V sub G and U sub G. So we're going to need those numbers because, let's see if I can, here we go. State 3 is a saturated mixture. It's under the dome. We're going to need to find X3, and so we will need to look up VF and VG at 70 psi and use the definition of quality to solve for X3, since we know that V2 equals V3. And the same drill for state 4. We're going to solve for X4. And then also in terms of our thermodynamic lookups, we're going to need U for each state, 1, 2, 3, 4. We'll be able to do that in MATLAB very quickly. Okay, so let's plan our work. We'll get VF and VG both at P1, 700 psi, and P3, 70 psi. And we'll also get UF and UG at those two pressures. Then we're going to work on the work out for 1 to 2. And that should be pretty easy, right? So it's the area of a rectangle. Mass, we know. Pressure 1, we know. We're going to have to watch our units. And then we will have V2 and V1 because we will have looked them up. Next, we'll solve for X3 and X4, the quality at states 3 and 4, because we're given, we know that V3 equals V2, V4 equals V1, and we've looked up everything we need to determine the quality at 3 and 4. Okay, so let's see. I just said that, didn't I? Next, we'll work on the work out from 3 to 4, since, and we could have done that at any point. We could have done that way back here, but this is just the way I decided to work on the problem. The work out from 3 to 4 is the mass times P3, which is known V4 minus V3. Well, that's, in this problem, that's going to be, let's see, V1 minus V2, isn't it? Okay. We're going to need to determine the internal energy U3 and U4 using the definition of quality that we just found. And then we will apply the first law, Qn minus W out equals delta U, for each of the 4 processes, and then we'll summarize the heat transfer and the work for each of the 4 processes. So there's the setup. We've done this before we've opened MATLAB. Okay, and this is my clue to go live. And so what I'm going to try to show you, a couple of things, is to start with a MATLAB program that you can download from Jay's Toolbox website. And this is the steam water functions that you will need. Going to use save as, and then start your own solution from that. And so you're going to be able to get the needed steam properties by calling a few of these custom formulas in MATLAB that I've built for you and for myself. So we'll go, that's my signal to go live, and there's a couple of things I've got to try to remember. Okay, so I'm going to minimize PowerPoint, and I'm going to go to my browser, and this is Jay's Toolbox Canvas site. And so let's see, Jay's Toolbox, I brought up the playlists, and let me scroll down. I have a playlist that's called MATLAB. If you click on that, what I want to suggest is that if you haven't done it yet, watch this 35-minute video on steam tables, and I tell you all about how to access the steam tables to access that particular MATLAB file. That'll be what you start with. Okay, and then let's see. And then I'll need to post this video to my playlist once I finish recording the video. All right, so that is my Jay's Toolbox YouTube channel. Next thing, now let's bring up MATLAB. So I've already brought it up, and I've opened up steamwaterfunctionsenglish.m. This is our starting point. And so notice here, I'm scrolling down, and these are all comments. I'm explaining what's available in terms of these custom functions. And then in this MATLAB file called Steam Water Functions English, I do a demo. I do a bunch of demos. So this file runs, and you can get a demo of how these functions work. Now you're going to wipe all those out, but you have to start with this, and then you're going to say save as. And I've done save as, and I've called it MATLAB011Prob3x55. So with this file open, you're going to drop down save as and save it to a new file name. So I've already done that. So I'm going to X out. Okay, so now I've got one MATLAB file open called 0355. And rather than dragging you through every step of typing, I've typed this all in and satisfied myself that I think we've got a working MATLAB program. Let's look at it. How did I create my prob355.m MATLAB file? First thing I started out with is a bunch of comments where I've entered the given information that we just reviewed. I've also, with a bunch of comments, I've sort of typed out what my approach is in MATLAB of how I'm going to solve the problem. This is a courtesy both to others and to yourself, because look, in a month or so, I'm going to forget what I did in MATLAB, and I'm going to need that reminder even to remind myself, much less others who might want to share this work. So here's my solution, the tried and true clear everything. And then let's see what I'm doing. I'm titling the command window output, result for problem 355. And then I'm going to enter my given values. And wow, for this problem, remember in your mind, there's only 3 pieces of given information. The mass is 1 pound mass. I'm putting in m equals 1. That makes sense. But notice how I'm using units too over here in my comments. P1 is 700. That's the high pressure of the cycle in PSI. And P3 equals P4 is 70 PSI, low pressure of the cycle. So that's my given information. And I've tried to select variable names that make sense. Okay. Now it's kind of for me, this is the fun part because it relieves me from the drudgery of interpolating in steam tables. So I'm going to need to study the custom function I've got for VF and VG. And when I study that, let me light this up here. Notice here, I need VF. And so V1 is going to be equal to VF. But the only function I can find is a function of temperature, not pressure. And my input number is a pressure. So I've got to figure out how to get the temperature at state 1. And so I remember enough about thermo that under the dome and at saturated liquid and saturated vapor, there's a special relationship between pressure and temperature called the saturation conditions. So the first thing I do in MATLAB is I find out what is T1. And so I go to my custom function tsat_, tsat_p, saturation temperature as a function of pressure with _ degrees F. I'm in English, and I'm entering my argument for this custom function is simply P1, and then I'm writing out degrees F is going to be the return value of T1. So I hope you see how that works. I had to go get T1 first using my custom functions. Now I can get V1 and V2, which are simply VF and VG at T1. I know I blazed through that, but I hope that's clear to you and you have enough experience understanding how to work with saturated conditions and pressure, temperature, saturation conditions. All right, next step. Boy, this is getting really easy in MATLAB. I got to remember I've got to find UF and UG at T1, P1, and here it is. I simply look up using my custom functions. U1 is UF as a function of temperature and BTUs per pound. So that's the name of my custom function. The input number is T1 in degrees F. Okay, so I've got U1 and U2. Next step in MATLAB, determine the work out from 1 to 2. Now, moving ahead, this doesn't have a whole lot to do with MATLAB. It has to do with engineering. I've got to remember my units. And so the first thing I'm going to do in finding the work out is convert P1, which is in PSI, to pounds per square foot. So I'm going to create a new variable called P1 LBF per SQFT. So that's the long variable name for P1 in pounds per square foot. It's simply 144 times P1, which is PSI. And notice my units, pounds force per square foot. So the work out is the integral of PdV, or M integral PD little v. So that's going to be M times the pressure in pounds per square foot times, since the pressure is constant, change in volume, V2 minus V1. And I recognize that my units are foot-pounds force for this variable, W out 1, 2. And so what I'm going to do in my solution is simply to keep the same variable name, but I'm going to divide it by 778. That's my conversion from foot-pounds force into BTUs. There's 778 foot-pounds force in 1 BTU. So this is the type of thing that you have to have in your head that really doesn't have a whole lot to do with MATLAB, other than you got to know how to do the math in MATLAB. Now in my work, I suppress all of these calculations going to the command window sort of until I'm done with a block of work, and that's what I do here. Summarize states 1 and 2 results, and so you can see it's very repetitive. I'm creating a dummy variable just called result, and I'm forming up a string, P1 equals, comma, number to string of P1, and I'm saying the units. And I'm doing this for P1, T1 in degrees F, V1, right? So I want to check my work, even in MATLAB, to see if my results make sense. So I'm printing out things I've looked up with my custom functions, and then I'm also printing out a numerical result, W out in BTU. So you can see how I'm doing that all in one block. And we're going to hit run, and I think it's going to work. All right, next, sort of the next block of work. Okay, I need to get VF and VG at 70 PSI because I've got to work on the quality of states 3 and 4. All right, so same drill. I'm given the pressure, but I'm going to need the temperature to look up VF and VG. So there's my function call to find the saturation temperature at P3. Okay. Same drill here. I'm going to look up VF and VG. And now, so I'm going to solve for X3. So X3, let's see. How would I solve for X3 in MATLAB? Well, it's just like doing it in pencil and paper. You remember that as a proportion, definition of quality, it's proportion. It's V2 minus VF, that's the numerator, divided by the denominator, VG minus VF. All of that at P3. So notice my variable names, VF at P3, VG at P3, okay? And I can then, it's like copy and paste. Now, X4, I copied and pasted X3 and jiggled the numbers, the subscripts around, became very easy in MATLAB to determine X4. Now that I've got X3 and X4, do you see that I can determine, whoops, I just talked about that. I'm recalculating V3 and V4 to criticize my own work. I don't think I had to do that, did I? Yikes, because V3 equals V2 and V4 equals V1. Okay, well, so shame on me for doing that, but it still works, right? Now, look up UF and UG at P3, right? So let's see. We've already found T3, so I've got there's my U sub F, my custom function. I'm gonna call it UFP3, UGP3, okay? And so I'm determining, so that's UF and UG. So in order to determine U3 and U4, I've got to use the quality. And so the quality is U3 equals X3 times UG plus the leftover amount, 1 minus X3 UFP3. Same thing on P4. So I'm sort of thinking in my mind as I'm going down the solution, shame on me for doing this work, right? I probably would have been more appropriate for me to have said V3 equals V2 and V4 equals V1, right? That would have been more efficient to have said that. All right. And so determine the work out. Let's see, from 3 to 4. Let's see, we're changing the pressure into pounds per square foot, just like before. The work out, it's the same drill. It's the mass times the pressure times the final volume, V4 minus V3. And then we'll divide that. That's in foot-pounds force per pound mass. Divide by 778 to get BTUs. And I'm saying, and again, shame on me. I see that for this is labeled incorrectly. That should be foot-pounds force. The mass times P times delta little v is foot-pounds force. And the workout is BTUs, not BTUs per pound mass. Shame on me. All right. And I'm hoping that I corrected that in my summarizing states 3 and 4. And I see that I did catch that. So notice here, the workout I'm correctly labeling as BTUs. Incorrect in my labeling as I'm going along. Shame on me. What's the last part of the problem? Use the first law for each process, Q. And so in my solution, I'm typing out in a comment, Qn minus workout equals M times delta little u, okay? And then I'm going that for each process. Qn from 1 to 2 equals W out from 1 to 2, already found it in MATLAB, plus M times little u2 minus little u1. Got it. Okay. And thank goodness I've got my units correct there. Next thing, work out for process 2 to 3. So to remember that in our pre-work, we identified that the work out from 2 to 3 is 0. So I'm going to be consistent in my MATLAB formulas. Okay. So Qn from 2 to 3 is W out from 2 to 3 plus M little m times little u3 minus little u2. Already done it in my pre-work. So Q from 2 to 3. Look at the repetition. And so when I'm doing I'm creating my MATLAB code, I'm doing a lot of copying and pasting and then changing subscripts. So first law for 3 to 4, very repetitive. Okay. And then first law process 4 to 1. And again, I typed out W out from 4 to 1 is 0. We got that from our planning. And then finally, I'm summarizing what I just did. All the numbers I got summarized, both heat transfer and work for each process. Finally, then I'm calculating the net work. That wasn't exactly requested in the problem assignment, but just for completeness, the net work is simply the sum of all the works done for each of the 4 processes. I'm calculating it, W net, and that's of course going to be in BTUs, and I'm going to print it out, W net. Now you say, whoa, where else? I've got more code here. This is the code that you saved from the source file. Look at this. It's a bunch of comments. It's got the list of custom function are available down below for both saturated vapor and superheated vapor. You didn't even use superheated vapor for this, but you've got the code in there. And then here's the function library. So this is what I've done a couple of months ago in creating custom functions so for example, here's what we used to look up the saturation temperature as a function of pressure. And so this is where you could go back to that video to see the background behind that. So it goes on and on. The file goes on and on and on, but that's just part of your save as. So you don't really need to look at that. So let's see. I hope this is going to run. And so I'm going to click run, and let's see what shows up in the command window. Oh, there it ran. Lightning fast. The result for problem 355. Here is that first block of work, found V1 and V2 from lookups, U1 and U2 from lookups, and calculated W out is positive number. Makes sense. Okay. Next block of work down states 3 and 4. I entered just as a courtesy 70 psi that was given. I'm printing out what's the saturation temperature at 70. Well, it's 302.833. Wow, that saved me from having to go to the back of the book. V3 as a check, sure enough, these are identically equal to V2. V4 is identically equal to V1. I solved for X3, which is 0.1. Okay, that it's some number between 0 and 1, closer to 1 than to 0. And look at this, X4 is nearly 0. So X4 is nearly a liquid. Okay, so that's kind of a good learning. Okay, and no units for X, right? So X is unitless. Okay, here's my lookups for U3 and U4, applying UG and UF. And I see that I did not print out UG and UF. That could be a courtesy that I should have added. Okay. W out from 3 to 4 is a negative number. Makes sense from the sketch we looked at. And then finally, here's the summary of all the works already printed out up here, and heat transfers that we calculated in the solution. Oh, and here's finally, W net is a positive number, 66 BTUs. Okay, so this file, it's not perfect, is it? I made a couple of little blunders. One, some in my comments, improperly stated units, and also in that solution, I solved back for V3 and V4, and shame on me, I should have just said V3 equals V2 and V4 equals V1. Okay, so that is the live demo, and if I run it, it runs again automatically. So let's see, let's go back to PowerPoint to finish up this video. We just went live. We got the needed steam properties using those custom functions. Hope I showed you how to do that. Move my image here. Okay. This was the beginning part of my, I did save as. Prob011Prob3x55.m. I'll try to go correct those blunders that I had and repost. Okay. Note, remember, comments, given information, comments, outlines of the solution. And then I went in and started with the given values and started writing my code. In my code, remember what I'm doing is I started by titling the command window output. Throughout my code in MATLAB, I was careful to suppress my data entry and suppress my calculations. And also in comments, that %, I had what my variable is and what are the units. And I tried my best to select logical variable names, V1, V2, U1, U2, and that type of thing. Okay, and let's see, what did I do on, I continued with units and comments throughout my code. And I'm thinking as I'm talking. I selected a variable name of UFP3. That would be UF at the pressure P3. I see I didn't do that for U1 and U2, but that's just, we'll just say that's just the person coding the MATLAB gets to pick his or her variable names that he wants or she wants. And then I applied the first law repetitively for all four processes and summarized my work. Okay. So here's the command window output. We clicked run, and this is the result. Notice how my variables are clearly stated. The numbers are clearly stated, but also I included units with each number reported. So this is good engineering practice that I really want to recommend you try to adopt. Okay. Oh, and so let's see. It says go live again. So I'm going to need to escape out of here if I can. Pardon me. Okay. And let's go to Canvas. So for those of you who have Canvas access to Jay's toolbox, we're going to go to Files. We're going to go to Tutoring. And let's see, let's click on the MATLAB folder. And by golly, I hope I saved this file. There it is, problem 355. And so you can click on this. It'll open in your Canvas browser. You can click download and you can possess this MATLAB file. I'll try to go clean up some things, the blunders, and repost it. Okay, let's see. Now I've got to go back to PowerPoint. Pardon my clunky behavior here. Click the download icon, load directly into MATLAB. Develop your own MATLAB problem-solving style. So remember, I share this simply to show you how I solved the problem. There's plenty of other ways to solve the problem, but I do want to recommend that you document your work as best you can. There's some advantages and disadvantages to getting good at solving thermo problems in MATLAB. Let's see, advantages. It forces you to create a disciplined solution and think through what you're going to do. It can speed the solution time for repetitive homework assignments, especially when you have to interpolate and getting thermodynamic properties. And this provides you with a solution template. It can give you a library, give you your own toolbox of MATLAB solutions to thermal systems problems. Disadvantages. It's a little awkward for a single document. So again, I'm trying to remind folks that a complete solution for a thermal systems problem is some stuff on pencil and paper or some type of document that shows you've started with a sketch and done some pre-work, documents your thinking. Then you're going to include MATLAB code to demonstrate that it's your work and not somebody else's work. And of course, the numerical results with units is the command window output. And so the combination of these things really is the entire solution. That can be a little awkward. And the other important disadvantage is that this work process is different than preparing yourself to do a quiz and a test, because in a quiz and a test solution environment, you're working pencil and paper and probably calculator only. And there may be even some restrictions on calculator work. But so that would be a disadvantage of just seizing on MATLAB and becoming a MATLAB guru with thermal system problem solving. Don't forget that you need to be preparing for quizzes and tests in order to perform well in class and get a good grade. Okay, so that's it. I hope this has helped you in a couple of ways. One is maybe help understand how to solve a thermo problem that involves thermodynamic property evaluation. Hope it illustrates how could you solve that in MATLAB and utilize these custom functions that I've created for you and myself that I've been using a lot, and also help you practice sort of a disciplined solution style. Also, it looks like I illustrated a couple of blunders. So it does illustrate that nobody is perfect, and it's important to go back and fix your blunders when you discover them. Hope that helps, and hope to see you next time on another MATLAB thermal systems solution.